Hello, my name is Rolando Chacon. This presentation is about cyclic loading in vertical stainless steel links, and together with my co-author Jan Nicolas Martinez, we developed this investigation at the Department of Civil and Environmental Engineering of the Technical University of Catalonia. This belongs to a vaster project called PINOX, which has already finished, about stainless steel frames subjected to static and accidental loading. Cyclic loading in vertical stainless steel links have been studied from two perspectives. The perspective of the material, stainless steel, material with a high resistance and ductility that is being assessed for its strategic use in dissipative zones of steel structures, and the perspective of the structure, eccentrically braced frames, earthquake-resistant structures whose dissipative zones are concentrated on their links, either vertical or horizontal, and their dissipation mechanism may be associated with shear, bending, or a combination of both. In this research project, eccentrically braced frames have been studied from the materials perspective, cyclic hardening, from the perspective of isolated horizontal links, isolated vertical links, and vertical and horizontal links that belong to systems. From the materials perspective, a vast experimental program on 40 specimens tested under different amplitudes of deformation strain up to 5%, under different protocols like companion, multiple step, or arbitrary, and that belong to a vaster program of a PhD thesis that is being elaborated by Lucy Lázaro currently. Here we can see the experimental test together with numerical simulation of such test under arbitrary loading, cyclic, I mean. And on the other hand, the analysis and the study of isolated horizontal links subjected to cyclic loading has also been addressed in previous research within the project, which has already been published, and these links, I-shaped horizontal links, have been studied under different configuration of stiffening of material, of slenderness, and of level of loading. When it comes to this topic, which is isolated vertical links subjected to cyclic loading, so several topics are worth pointing out. First, a review of the material and of why inverted vertical links. Second, some numerical models for the material and for the structures. Third, we present a parametric study on isolated vertical links, and then some results and discussion of such results. So the material, as we mentioned, is about stainless steel. It's an alloy which contains a high content of chromium. Important characteristics for this study is the rounded sigma epsilon curve. Okay, and also one of the characteristics that is relevant here is the cyclic hardening. Stainless steel hardens when it's subjected to cyclic loading up to certain points, and it needs to be properly addressed when modeling. If we move now to the geometrical classification of the links, geometrical and structural, the links, either horizontal or vertical, are classified according to a parameter called ρ, which is the relationship between the length of the link and the ratio between the plastic moment and the plastic shear resistance. This ratio ρ generates that the link may be classified as short, as long, or as intermediate. If they are classified as short, the primary failure mechanism is associated with shear. If they are classified with long, as long, their primary failure mechanism is bending, And if they are intermediate, of course, there is an interaction of both shear and bending. And so this is a classification which is valid defined in Eurocode 8. So some failure modes have been presented in the literature. Okay? The number of possible collapse mechanisms of eccentrically braced frames is very high. At each story, yielding can develop in links, in beams, in columns, and in diagonal braces. So design looks for the failure mode that is concentrated on the link. Okay, and this is something that has already been studied by researchers. Also, something to mention is that the numerical models that are implemented in stainless steel subjected to cyclic loading require proper understanding of the type of hardening that is included in the model. We can define hardening as isotropic, in which the yielding surface expands together with the uniaxial load that is given. It may behave as kinematic hardening, in which the yielding surface does not increase in size, but it moves according to the cyclic loading. But in this case, stainless steel, austenitic stainless steel, exhibits both components. Exhibits isotropic hardening, but it also exhibits a certain degradation with the cycles, which needs to be reflected in the numerical modeling. This has been properly described using the Chabocci model, okay, in which there is a component which is isotropic, there is a component which is kinematic. Numerical models from the perspective of structure, we have developed and studied beam-based models in which all elements are defined like a big structure, okay? And in this big structure, a pushover analysis is performed. This pushover includes vertical loading and horizontal loading according to a certain pattern. And then we can also focus on more detailed structures in which we analyze isolated vertical links. Okay? These links are subjected to cyclic nonlinear analysis, and the models are more shell-based. Imperfections and residual stresses are included in such detailed models. So we have parametric study that includes system levels, in which certain different characteristics are studied at a system level, and also parametric study that is developed at member levels, okay, with a detailed vertical link. For understanding this parametric study, we need to understand that first of all we develop a global system, pushover analysis, we obtain the response curve, and in this response curve for different configurations we detect 3 levels of loading. In the global analysis we detect the maximum load, which generates a certain displacement delta max. We divide this displacement by 2, obtaining 0.5 delta max, and we multiply this displacement by 1.5, obtaining another displacement, a higher displacement on this response curve. So let's keep in mind these 3 values of displacement of the system according to the global analysis. With these values, we go to provide cycles of loading to the link in a detailed way, in a detailed model, and this link will be subjected to a delta which is related to 0.5 delta or 1.5. So we developed a parametric study in which variables such as material, stiffening, link length, and delta, which is the level of loading, and with a profuse variation, we can have some results. For the case of the global response, we can see here in the slide that the short, long, or intermediate elements provide different stiffness, different strength. This is expected. Okay. When it comes to results on isolated members subjected to a monotonic um, loading, you can see Vomis stresses in which we can also see the corresponding shear-like or bending-like failure mode. And then when we come to the cyclic loading, here we can see in the slide 9 pictures corresponding to short, intermediate, or long links, and corresponding to stainless steel and carbon steel for the sake of comparison, in which we have three levels of loading: 0.5 delta, 1 delta, and 1.5 delta. For the former, we can see that the response is quite linear in all cases, especially in long. There is a certain drift in the linearity and for the case of short elements, which were stiffer and in which displacements are more reduced, of course. And for the case of 1 times delta, we can see that in general, stainless steel, which is the blue curve, outperforms the orange curve, which is a comparable carbon steel. And then for the case of 1.5 delta, there is a clear difference between the cyclic behavior when it comes to very high levels of loading compared to the cyclic behavior when it comes to the maximum capacity obtained in the global response. So to conclude, a study of the structural response of austenitic stainless steel vertical links was carried out. The study is based on an initial understanding of the cyclic hardening of stainless steel, the global analysis of EBF, and the development of a fully Gymnia analysis. So this parametric study was conducted with a total of 36 models, including both stainless steel and carbon steel links. For different level of displacement and different level of or amplitude. Austenitic stainless steel can develop higher strength and ductility. It's a good idea to use it as a replaceable link in eccentrically braced frames. However, further studies involving experimental behavior of the material are being developed. Structural questions are being treated by the research group, like which is the benefit of using stainless steel in dissipative zones in earthquake-resistant eccentrically braced frames? Does this overstrength provided by the stainless steel affect the non-dissipative zones? So the design of hybrid stainless steel carbon steel dissipative non-dissipative zones ought to address these questions accordingly. So with that, I end my presentation, thanking to the funding agencies in Spain for the project PINOX stainless steel frames subjected to static and accidental loading.